Hi students, today we are going to discuss tutorial 2 for UO1. In this tutorial, we will cover different types of flow meters. In topic 1 lectures, if you have learned by yourself, there are a few types of flow meters used for the measurement of flow rate or fluid flowing inside a pipe. Can you give me some of the names of these flow meters? Pitot tube, venturi meter, orifice meter, rotor meter, yes. Okay, so in today's tutorial, we will cover the details on how to calculate for venturi meter and orifice meter. Now let's take a look of this venturi meter structure and try to understand how it is used to measure the flow rate. Okay, so for flow rate measurement, if let's say you have a tap water, you open the tap, you collect the amount of water in certain time, will give you a volumetric flow rate. But if the fluid is flowing inside the pipe, how do you measure the flow rate inside a pipe? Let's recall the Bernoulli equation you learned before, which is V1 plus Z1 plus P1 equals to V2 plus Z2 G plus P2 over rho, right? Okay, so now if you see this below here is the venturi meter where the fluid is flowing inside the pipe. Then venturi meter means there will be a gradually change of diameter to throat. So the throat will have a very small diameter D2. The pipe itself, the diameter is D1. Okay, then there will be a gradually decrease in diameter, then gradually increase back to the pipe diameter again. Okay, so due to the change in the diameter, right? So it means the velocity at point 2 will be higher or lower? Will be higher because the diameter is smaller. So what does this mean? If you check the Bernoulli equation, we don't have the potential energy. So if the velocity is higher, it means the pressure will be lower. So the same thing for point 1, the velocity is lower, so means the pressure is higher. Instead of measure the flow rate of velocity directly inside the pipe, we install a manometer below the pipe. Okay, we call this manometer. This manometer is used to read the pressure difference between P1 and P2. Now the P1 is higher, right? So this pressure will push the liquid here. Usually the indicator liquid we use a higher density will be mercury, so that the P1 will push the mercury to rise up here. So you will have a reading here, okay? It means that we don't directly measure the velocity. Instead, we measure the pressure difference between 1 and 2, which can give us the final velocity. So from here, you can see that the pressure difference actually can be calculated. The pressure difference can be calculated by delta P will be rho mercury minus rho water G delta H. So this is your delta H. Okay, then this is the pressure P1, this is the pressure P2. Okay, now if you understand how it works, finally you can see this will be the formula to calculate the velocity at point 2, means the velocity at the throat. So this is V2, it's not V1, it's V2. So if you want to know what is the velocity inside the pipe, you still can apply A1 V1 equals to A2 V2 once you determine the V2 here. All right, so this is how a venturimeter works. So let's come back to the question now. So you can see from the question, water is flowing, right? Then you have this 2-inch schedule 40. So this one means you need to check the pipe table to find the exact inside diameter of the pipe. Then the flow rate of water is measured by a venturimeter. Then the throat diameter is 20 mm. So this is D2. Then manometer reading is 250 mm of mercury. So it means this is delta H is 250. Now you need to calculate the volumetric flow rate. Okay, so if you understand from here how the venturimeter works, you will understand how to apply this equation here to find the velocity at the throat. Before that, we come to check the exact diameter. This is the pipe table. What you need to do is you need to check this column. So the inside diameter in mm. For 2-inch schedule 40, you check from here, you will find the reading of the inside diameter will be 52.5 mm. So this is your pipe size, inside diameter. Okay, so with that, if you read from the table just now, you can see for 2-inch schedule 40 pipe, the inside diameter is D1, convert to meter will be 0.0525. So you can use this to calculate the factor here. You need to use later for the calculations of velocity. You have a D2 over D1 ratio, right? So D2, because this one you convert to meter, so D2 you also convert to meter. So this is the factor you are going to use later for the calculations of V2. Then calculations of pressure difference, delta P, will be rho mercury minus rho water, G delta H. Please take note, this delta H you also need to convert to SI units in meter. So finally, this one will give you, the pressure will be in the unit of Pascal. Okay? Please also take note, inside the velocity formula, below here you have a density, right? So this density refers to the density of fluid. Now it's water flowing inside the pipe. And also take note, the units for the pressure I mentioned is Pascal. We have covered this in tutorial 1 already. So means on top, you have a pressure difference in Pascal. Bottom, you have a density units. So if you convert this finally into basic units, for Pascal is Newton, okay, Newton per meter squared, right? Then over this. So finally, you will find the units of this term will be meter square per second squared. So after the square root will give you the units for velocity is meter per second. So this is on how to find the velocity. Please take note, after that, you need to use A times V. So the A, please take note, you need to use D2 squared here. So you cannot use D1, all right? So after you find the volumetric flow rate in meter cube per second is quite a small number, 2.45 times 10 to the power minus 3. Okay, so this is how to calculate the velocity. Then from the velocity, you are able to calculate the volumetric flow rate. Then if let's say you want to find what is the exact velocity inside the pipe, how to find? You can still apply continuity equation. A1 V1 equals to A2 V2, right? Now you have V2 already, you have A2, so you can find V1 directly. Okay, so just to repeat for this question, for venturi meter, okay, the equation here, this is for venturi meter. The velocity you calculated here is the velocity for the throat. So means D2, okay, don't forget. Then the delta P here, the pressure, you can use mercury density minus water, G delta H to find. And then this one is fluid flowing, water flowing inside the pipe. Okay, so this is the points I want to highlight. Don't use wrongly. The density below here, you cannot use the density of mercury. You must use the density of water instead. So this is for question 1. Now let's move on to question 2. Question 2, very similar. Now you have an orifice meter. Please take a look at the structure here. For orifice, there's no gradually change of diameter of the pipeline. Instead, there's a plate here. There's a plate here inserted into the pipeline. So on this plate, there's an opening here. So this opening, we call this orifice. So other parts will be quite similar because there's a sudden change of the pipe size here, right? So there will be a flow velocity change through here as well. We call this DO. Then the pipe diameter itself is D1, okay? So the same, we will install a manometer below here, all right? So which will measure, this one will be mercury again. We will usually use mercury because mercury density is higher, so they will stay below here, right? So there will be a pressure difference between 0.1 and 0.2, and the velocity measured will be at the point here at DO, okay? Now the question said the crude oil is flowing, it's also liquid, right? Then this is the pipe. You will need to find what is the exact diameter for this 4-inch schedule 40. So you will go back to use the pipe table again. Then when the flow rate is 0.02 meter cube per second, what is this? This is a volumetric flow rate, Q dot, right? Okay. Then it's mentioned it's desired to have a pressure drop reading across the manometer, which is equivalent to 0.95 times 10 to the power 5 Pascal. Equivalent to, it means after you take your reading of from the manometer, you calculate, actually you can calculate the delta P will equal to this. Okay, so you no need to calculate delta P by rho mercury minus rho water G delta H again. You can directly use this. So this is your delta P directly. This one is delta P. You can use later. Okay. So the formula is more or less the same as a venturi meter. We just use a different symbol. We use VO for velocity at the orifice. DO is the diameter at the orifice. Okay. And the question here asks you what orifice size should be used. So means that you don't know the diameter of the orifice here. This is very different from question 1. For question 1, you know the throat diameter, but here, you don't know the orifice diameter. So it means inside here, I have an unknown. This diameter is unknown. Now I put a question mark. And from the volumetric flow rate, you know, I can write VO as volumetric flow rate over area, right? So inside this area, I have a DO as well. Please take note. Here, you cannot use the pipe diameter because this V we find is VO. Okay, so this diameter must be DO. All right, So here you have two equations. One equation is for the orange phase flow meter. Inside here, DO is unknown. Another one, I use volumetric flow rate over area. I also have a DO unknown, all right? Okay, so from here, you can write the equivalence. Then the 4-inch Schedule 40 pipe, you can use the pipe table to find the D1 is 0.1023 meter. This is a pipe inside diameter, okay? Then from the above two equations, you can write a balanced equation. Both sides, DO is unknown. So it means the following part, you are going to solve a simultaneous equation to find the DO, which is unknown, okay? Please also take note, here you have this 900 is actually the density of the crude oil flowing inside the pipe. And this value of delta P is already given directly, this one. You no need to calculate further, it's already given. So you can directly use it. All right, so the following part will be more mathematical work on how to solve these two sides mathematically. We just write step by step to help you to understand. Okay, so we calculate the square root first. Okay, then we get this value 14.53. The next step, I want to remove this square root. How to remove? Then we have to we have to take a square for both sides, right? So once I take a square, will be like this below. So the below DO will become 4. Okay, so on top, I calculate this will be 8.863 squared. Then below here, I will remove the square root. Now what is this 9131? It's from here. It's 1 minus, okay, 1 over 0.1023 power of 4, then DO 4. So I calculate this value will give me this. Okay, so I substitute this value into here. Then the next step, you cross multiply this. Okay, you do some mathematics. Then one side you have a DO power of 4. The other side you have a DO power of 4, right? Okay, so finally you combine these two, you divide it to this side, you will find DO 4 equals to this 7.673 times 10 to the power minus 6. Okay, then after that you divide it by a power here, 4 over 4, then this side is 1 over 4, okay? So you have a DO. So this part, finally, you will find DO equals to 52.6 millimeter. Is quite small compared with the pipe size. So this part is more mathematics. The key point for this question will be, if we go back here for a while, okay, you need to understand the velocity calculated by flow meter here is the velocity at the orange phase, okay? And also, if you use this velocity by volumetric flow rate given over area, then this diameter, you also need to use the orange phase diameter, okay? You cannot use the pipe diameter. So if you use the pipe diameter, what do you have? If you use the pipe diameter, it means you are calculating V1. If you use Q over pi over 4 D1 squared. This V1 is not VO, it's a different thing. Okay, so please try to understand this part. So this is for question 2. Question 3, you are given different types of valves. you have a gate valve, plug valve, needle valve, safety valve, relief valve, and check valve. You need to choose a suitable one for the following function. Okay, so this part, I hope you have already studied the polymer slides and videos. From there, you should understand how each type of valve works, okay, and the structure of the valve. So try to understand the particular function for each type of valve. For example, here, fine regulating of flow, you can only choose needle valve, right? So because the needle valve, the structure is the end point, there's a needle type of end, which is very fine. So when you adjust the valve, it means you are doing fine regulating, okay? Then other types, for example, handling of mineral ores, you can choose the plug valve. And the third one, handling of pressure with the high pressure, you need to release the pressure. So usually you would need to use safety valve or relief valve. And for throttling, the given valve is not suitable. Usually, if you check from your lecture notes, will be more suitable to use a globe valve or diaphragm valve for the throttling. Throttling is to change the pressure. The last one is preventing the reverse flow, is the check flow. If you studied the video, you watch the video, you can see for check valve, it's very special. There's a swing which can open only in one direction. So it means the flow can only follow that one direction when the swing open. All right, so can prevent the reverse flow. So for this type, I hope you can have a better understanding after you watch the video, okay? And also you have given one assignment. From the assignment, you study some of the valves you can find at your home. You will have a better understanding on how it works and how it is applied. Okay, question 4. Question 4 is a performance curve. Okay, this is performance curve for centrifugal pump. So for centrifugal pump, the performance curve is quite important. This one means how the three parameters, head, H, power, P, efficiency, eta, changes with volumetric flow rate. So the x-axis here is the volumetric flow rate. The y-axis, you have three parameters. Please take note, especially for the efficiency, you can see there will be an optimal point where the efficiency will be the highest. So it means, it doesn't mean that the higher the volumetric flow rate, the higher of the efficiency, okay? So there will be the optimal point for the operation. So it's better if, let's say, you choose a pump, you want to have the highest efficiency, you should control the volumetric flow rate properly. Okay, then the head of the pump will decrease with increase of volume. The power will increase with the increase of volumetric flow rate. Okay, so this is the question 4. Now we have finished all 4 questions.